Right, so Assalamualaikum warahmatullahi wabarakatuh, and a very good day to our lecturer, Professor Dr. Sharifah Sakina, our lecturer for subject linear algebra and numerical methods. As for today, me and my teammates will be presenting about our final project for the subject, which is numerical methods, where we choose a problem and solve it using bisection method. So dividing it into three parts. The first one being introduction, where we briefly talk about our background to the problem we have chose, and the second part being numerical consideration, where we get more specific into our solution and how we use bisection to solve it. And lastly, the result, where we include the iteration and also the coding we had created specifically for bisection. So before we get into that, let us just introduce ourselves first. My name is Awfa Izzah Binti Azhar.
Hi, my name is Farisah. Okay, so this is the introduction and background. So we choose bisection method as our numerical method project. So the bisection method in mathematics is the root finding method that repeatedly bisects the interval and then chooses the subinterval in which the structure must exist for further processing. We solve our everyday problem by using bisection method. This is how it works. Bisection method is based on intermediate value theorem. According to the theorem, if there exists a continuous function in the interval a and b, and c is any number between function when we put a function in, we put a in the function and b in the function, then there exists at least one number x in the interval such that fx equals to c. The intermediate value theorem can be represented graphically as follows. So the problem we choose, making a bookshelf to carry books that range from 8.5 inch to 11 inch in height, I would take up 29 inch of space along the length. The material is wood having a Young modulus of 3.667 MSI, thickness of 3 per 8 inch and width of 12 inch. We have to find the maximum vertical deflection of the bookshelf. The vertical deflection of the bookshelf is given by, those are the function. So those are the equation where x is positioned along the length of the beam. Hence, to find the maximum deflection, we need to find where the dy dx is and conduct the second derivative test. Why bisection method is needed? Bisection method is required to solve this problem as it is always convergent. Since the method brackets the root, the method is guaranteed to converge. As iterations are conducted, the interval gets halved, so one can confidently guarantee the error in the solution of the equation.
Right. Okay, so moving on to numerical considerations, I will start with how to apply to find the position x where the deflection is maximum. Then we conduct 3 iterations to estimate the root of the above equation. And lastly, we find the absolute relative approximate error at the end of each iteration and the number of significant digits at least correct at the end of each iteration. So I will start with the method discussion. From the physics of the problem, the maximum deflection would be between x equals to 0 and x equals to L. So where L is the length of the bookshelf. Therefore, so we will create this 0x between 29. So we will just let's assume that XL is 0 and XU is 29. So what we do is we check if the function changes sign between XL and XU. So it's like we insert it into our equation earlier. If we insert 0 into our function earlier, we will be 507. And if we insert it into fxu, which is 29, we will be receiving an amount of 0.018 0.826. Hence, fxl and fxu, which is f4 and f29, means that there is at least one root between xl and xu that is between 0 and 29. So let's move on to results. I will be starting with the first iteration. This is the formula to count the estimate of the root, which is our xm. So starting adding xl and xu, 0 plus 29 and divided by 2, which is 14.5, and we insert this root into our function, which is of negative 1.4007 multiplied by 10 to the power of negative 4. So we will be doing this fxm, fxu, which is f14.5 and f29, which is a negative 1.4007 multiplied by 10 to the power negative 4, and 0.018826 is less than 0. So the root is braceted between xm and xu, and that is between 14.5 and 29. Therefore, the lower and upper limits of the new brackets are this is the new xl and this is the new xu. But at this point, the absolute relative approximate error cannot be calculated because we do not have a previous approximation. So we will be moving on to iteration 2, 29 divided by 2, which will give us an amount of 21.75. So insert that into our function earlier, f21.75, and will give us an amount of 0.012824. So as we did previously, multiply the two of them, fu, which is f14.5 and f21.75, which is negative 1.4007 multiplied by 10 to the power of negative 4, and this amount, which is 0.012824, still lesser than 0. Hence now the root is braceted between xu and xl and xm, that is between 14.5 and 21.75. We are not able to calculate the absolute relative approximate error at the end of iteration 2, being this is the formula, and so we insert 21.75 divided subtracted by 14.5 divided by 21.75 multiplied by 100, and we will be receiving an amount of 33.333%. We have to move on to iteration 3, where we start with the estimation of the root being 14.5 added with 21.75 divided by 2 gives us an amount of 18.125. Inserting that into our function, fxmf 18125 will give us an amount of negative 6.7502 multiplied by 10 to the power of negative 3. Repeating the previous steps, fxm and f 18.125, which is negative 1.4007 multiplied by 10 to the power of negative 4, and 6.7 negative 6.7502 multiplied to 10 negative 3, still lesser than 0. Hence now the root is braceted between xl and xm, that is between 14.5 and 18.125. Therefore, now the lower and upper limits of the new brackets are being xl 14.5 and xu 18.125. So now we count the absolute relative approximate error, which is this at the end of iteration 3 being 18.125, subtracted with 21.75 divided by 18.125 and multiplied by 100, we will be getting a 20%. Yet still the equation as the absolute relative approximate error is still greater than 5%. So we conducted 7 more iterations. As you can see, at the 10 iterations, we are left with the XM being 14.585 and the absolute relative error being 0.19417. So at the 10th iterations, we see the absolute relative error is 0.19417%. Therefore, the number of significant digits at least correct is given by the largest value of m, for which lesser than 0.5 multiplied by 10 to the power of 2 minus m. So we know the absolute relative is this one, so we just fill that in. 7 lesser than 0.5, 10 to m, and we move this forward, so then 10 to m, and to solve this we have to incorporate log, so move this forward, so we are left with log 0.3835 less than 2 minus m, and now we are left with m2 minus log 0.38835 equals to 2.4108. So therefore, m equals to 2. The number of significant digits at least correct in the estimated root of 4.585 is 2. And that's 10 iteration, and that's from moving on to MATLAB coding.
Okay, this is the MATLAB coding that we made. This is the full coding we created to solve the bisection method. So first, first we input the function, the function that we mentioned ago, and then we put the lower limit and the upper limit. So if the user had inserted an amount that is above 0 for the lower limit and the upper limit, the system will not be able to calculate it and will print the line wrong choice. Moving on, if it doesn't have a problem, it will display all the calculation based on the iteration that we set on, and that is 10 times iteration. So this algorithm will decide whether to use the data from the previous data as a lower limit or an upper limit, so we can look where the error is and continue with the iteration. And that's it.
Let's just do a quick MATLAB coding demonstration.
Yes.
I have the coding with me here, so I just will run it. So we have a function, so it will ask us to enter the function, so let's just enter function. And for lower limit, we have our lower limit as 0 and upper limit is
9. Yeah.
and it will print out all of it, the lower limit, the upper limit, the XM, and also the FXM. That concludes our presentation. Thank you so much, madam.
Thank you so much.